right. Welcome, everyone. My name is Konrad Kamiński. I work for Allegro. So Allegro is the largest Polish e-commerce company. And today we're going to talk about Kotlin Native. So what is Kotlin Native and what things you have to know before you start using it? So first I have one question, like how many of you have used Kotlin on JVM or on Android? Okay, that's quite a few. That's great. I ask because, well, first of all, there will be some live coding here. And second of all, I will compare some things with how Kotlin works on JVM and how Kotlin works on Kotlin Native. So what is Kotlin Native and what are we going to talk about? Well, first I'll talk about what is Kotlin Native essentially and why is it different than Kotlin, why it's not just Kotlin. And then we're gonna talk about some few specific things which are different on Kotlin Native, especially about concurrency model, memory model, and the interoperability with the C language. So what is Kotlin Native? So this is you could say, a tool set or a compiler which allows you to create native applications. So in the end, you will have native binaries on many platforms. So right now, there is like quite a lot of platforms actually supported because you can create applications for iOS, for Linux, for embedded devices, for Android, which means that you can create native applications on Android with the NDK, and also for things like WebAssembly. So there's quite a large number of those platforms. So how is it different from the Kotlin we know on JVM? Well, the Kotlin JVM compiler actually is composed of two parts. There's the sort of so-called front end and back end. So the front end, it actually takes the source file when you compile your Kotlin application. It takes the source files and it translates it into something which is called Kotlin Intermediate Representation, the Kotlin IR. And then the backend part of the compiler takes this Kotlin IR and compiles it down into Java bytecode. And so Kotlin Native, it reuses one of these parts. So essentially what it does is it takes the output of the front end, so this Kotlin IR, and it actually translates it to a different IR, which is called LLVM IR. So what's LLVM? LLVM is like a set of tools or libraries which allow you to create applications or to compile applications in many languages on many different platforms. So LLVM actually supports all of those platforms that you've seen before, which are supported by Kotlin Native. But it also supports some more platforms, like, for example, GPUs. So in theory, if you could write applications which run on GPU with Kotlin Native, it doesn't work out of the box. But if you are willing to do so, you can actually take the source code of the Kotlin Native compiler and add some few things. And in theory, you should be able to run it also on GPU. And LLVM is actually quite stable and quite a mature product. It's been used for a couple of years now, maybe even 10 years. If you use things like Clang, the C and C++ compiler, on macOS, for example, or actually anywhere, it actually uses LLVM underneath. So it's quite stable and mature. And LLVM takes this intermediate representation and it compiles it to the native binaries. So we have these 3 steps. But this actually all happens under the hood. If you use Kotlin compiler, Kotlin Native compiler, you don't have to invoke all those 3 steps by yourself. They are actually done by the Kotlin compiler itself. So you just provide your source file, and at the end you get the binary. So what else is in what areas the Kotlin Native is different, or what else does it have that Kotlin JVM doesn't have? So one thing is the access to the platform APIs. If you use Kotlin on JVM, you have access to the Java standard libraries and all the libraries actually that are available to Java. But on native platforms, you don't have access to these libraries. But you have access to the native libraries. So for example, on macOS or on Linux, you have POSIX libraries. On Windows, you have Win32. So essentially, you have the access to the native platform APIs. And if you want to use some library which is available, but you only, for example, have source files, or if you use it in C language, you usually have header files and the library itself in the binary format. You can actually use it in Kotlin also, because Kotlin Native provides you tools which allow you to just take these C header files and it makes a Kotlin library which you can use in your applications, Kotlin Native applications. And the same thing applies to Objective-C and Swift. So if you're doing something on iOS, for example, then you should be able to use Kotlin Native with this. And there's also one more thing which is different from, for example, applications written in C or C++, which the applications written with C and C++, they don't run on virtual memory, on virtual machine. So you have to worry about memory management for yourself. So there is no such thing as garbage collector, at least not yet, in these languages. But in Kotlin Native, you have actually a garbage collector, and it's actually a nice one. It's a bit better in some ways than the garbage collector you have on JVM, for example. So with all of this, now, how is it different from, apart from these things which actually they have to be in the native language? What else? What differences are there? So the main difference is the concurrency model and the memory model. So on JVM, we have, and it's not only on JVM, it's actually quite popular model of concurrency. We have threads. So we have threads, they run concurrently, and they access objects which are shared across threads so that multiple threads can actually modify the same object. And this actually creates quite a lot of problems. So what we usually do is we try to synchronize the access to these objects. And this is actually it's quite hard to write a correct concurrent code. And usually we end up with things like race conditions or deadlocks. And this is why a lot of high-level APIs are quite popular and try to fix this problem. So if I say about high-level APIs, I mean things like completable future and executors on JVM. Or on Kotlin, we have coroutines, which also allow you to write quite safe concurrent code. So to some extent, this solves the problem. But there is also a different side of this concurrency model with threads. So if you have a garbage collector, then at some point it has to be executed. So it has to find all the objects that are not used by your application anymore. And what it usually does is it tries to traverse the whole tree of all objects and mark all those which are used so that these which are not used are not marked, and it just reclaims the memory, which is occupied by them. But if you have concurrently running applications which modifies these objects, then it's really quite hard to write this kind of garbage collector. This is why often with garbage collectors we have these stop the world pauses, which essentially mean that your whole application is stopped for a while so that the garbage collector can do something. And in that phase, the garbage collector is certain that nothing will change, no object will change. And this actually, it poses quite a problem if you have an application where you don't want to have these pauses, then it's quite difficult to achieve that. We have these new garbage collectors, these pauseless garbage collectors, which are quite sophisticated, and they try to minimize this stop the world pause, but they're actually quite complex machines. So it will be quite difficult to implement such a thing for Kotlin Native. So the Kotlin designers, they decided that they will go in a different way. And the concurrency model on Kotlin Native is based on workers. So you can. I mean, in Kotlin language itself, there is no concurrency primitives built in. They could write, the Kotlin designers could start from scratch. So they design workers. Workers are, you can think of workers as sort of an actor, like in actor model. So an actor is some entity which has a queue of things, of messages, and it takes those messages one by one and processes it. And this is quite a simple design. These actors are single-threaded, so they don't have to care about that someone else will change something in this message, or it modifies the state of the actor. And so a worker in this manner is similar. It also has a queue. It has a queue of jobs, and it takes those jobs and tries to execute it one by one. Now, the implementation of a worker is actually platform dependent, because on some platforms, you have threads, for example, on Linux or macOS or Android, you have threads. So there is usually a one-to-one relationship between a worker and a thread. But there are some platforms which don't have threads. So if you think about, for example, embedded devices, they usually don't have this thread model. But from the point of view of a developer, you actually only have access to this worker. So you don't really care about what the implementation is. So how does this worker look like? So here you can see this basic functions and the worker class itself. So essentially, to start a worker, to create a worker, you call a start function. It gives you a new worker. And then you can submit a job to this worker. There is this quite fancy execute function with 3 parameters. We'll get to why this function is so complex. But the most important thing is a job. So a job is something which will be executed in this worker. So in a different thread, for example, on a platform which supports threads. So this job will be executed. The result of this job will be actually delivered via this future result of the execute function. The future is very similar to the future we have on JVM. We can read the result from this future, or we can pass a function which will be called once the future is the operation is completed, and there is a value available from that future. There is also something called producer. So the input to your job is actually a value which is produced by a producer. So we have this 2-step procedure. First there is a procedure called, and the producer called, and the producer is called from the thread that calls the execute, and then the value provided by the producer is passed as an input to the job. And so the question is, why is it like this? And we're going to get to this in a moment. But first, let's try to create a simple application which uses workers and see what kind of problems we may have. So, I have some problems here with display. Let's make a mirror. Okay. So can you see it, or like in the last row, do you see it, or should I make it like larger? Larger. Okay. Try to. Okay. Okay. Fine. Right. So we're gonna create a worker. So we call worker start, and this will give us the worker, and then we'll just execute. So we will pass a job. We're going to use the safe mode right now. We have safe mode and unsafe mode. We'll get to what it means. We're going to use safe for now. Our producer. Well, let's create a class conference, because we were at the conference, that we will and we will pass this as an input to the job. So our conference will have a name, and it will have a year when it's held. And let's make it more explicit. So let's make what's the name? Mode. Okay, so let's make mode is this. To make it more explicit, producer will produce a conference. So it's GeeCON, and it's 2019. And we'll have a job. So a job will have an input and an input. Let's in our job, let's print out the input. But to make this printing even better, let's define our own logging function, which will print also the name of the thread or the name of the worker, or the main thread, which actually executes this logging. So we're going to create a simple logging function. It's possible to access the current worker, or the worker that your code runs in, with by accessing the current property on the worker. It can be a null value. So we have to make a save call, and let's convert it to a string because ID is an int. And if it's a null value, then let's make it main, so that we will see that it's a main function, main thread. And let's do some padding here. Now it looks complicated, but it's just so that the output is easier to read. And then let's add our message. So here we're gonna print out that input is. Let's print out the input. Our job will return OK. So the execute actually returns a future. So let's assign it to a future, and let's print out the result of the future. As future result. Okay. So this should be everything we need. Actually, I'm using here IntelliJ IDEA, the community edition, so you can all try it at home for free. There's a Gradle plugin for Kotlin Native, which allows you to compile your native applications. And I'm actually using a Gradle plugin to compile and execute the application here. Okay, so we can see here that the input in our worker is a conference, and the result is OK. We should use log here. So it worked as expected. So let's try to make one change. Let's make this conference a local variable of main. So a conference will be created here. We will return this conference in our producer. And so the application should roughly be the same as before, except for the fact that we are actually creating the conference here. And we can actually see that it fails. So let's see why it fails. So there's an exception thrown here. It's actually thrown at the time that you call execute, and it's called illegal transfer state. So this transfer is actually you can immediately see that here is a transfer word and here is a transfer word. So there is something going on here. So to understand actually why this doesn't work, this small change, we have to talk a bit about the memory model that's in Kotlin Native, because it's connected with the concurrency model. So let's get back to our presentation. Okay. Right. So memory model. So the problem with having mutable objects which are modified by concurrent threads is that you have to synchronize access to these objects. So what if we allowed a model where you either have immutable objects or you have mutable objects, but they are only allowed to be accessible by one thread at the same time? Then we would have really no problems, because, I mean, immutable objects can be accessed freely and safely from multiple threads concurrently, and there is nothing unsafe in this. And if we allow it to access an object by only one thread at a time, then the other threads don't have access to these objects. Then again, it's like a single-threaded application. So it's also quite safe. And this is the way the Kotlin designers designed the Kotlin Native. So in Kotlin Native, you can either have an immutable object or a mutable object which is accessible by only one thread. So, but at the language level, there is no such thing as immutability. So we use Kotlin on JVM, and we can freely modify objects. So this is why right now in Kotlin Native, the immutability is actually a runtime property. So we can make any object immutable. Well, I could say you can mark it as immutable. And it's called freezing in Kotlin Native. So you can take an object, you call a freeze function. This function is an extension function which is available on any kind of object. And you can freeze it. And after freezing, this object cannot be modified by any thread. You can always check if an object is frozen by calling reading the isFrozen property, and you can also make sure that that a particular object will never be frozen. And freezing has two properties. So one is that it's a one-way ticket. So if you freeze an object, you can't unfreeze it. It will be frozen till the end of the world or of your application. And it's transitive, so it means that if you freeze an object and this object has a reference to a different object, and this object has a reference to a different object, then if you freeze the first object, the whole subtree of objects will be frozen. So we have this subgraph of objects which all of them are frozen. And there are some objects which are frozen always, like, for example, strings. Like in Java, in JVM, strings are sort of read-only or immutable. So without doing any hacking, you can't really change them. And in Kotlin Native, strings are frozen by default. You can't unfreeze it. You can't have an unfrozen or mutable string. So let's try to modify our application so that the conference that we pass to that we return from the producer is frozen. Let's see if it works. No. Okay, let me try this one. I have a problem with changing these things. Okay. Okay. Okay, fine. So what I'm going to do is first let's print out if the conference is frozen at the beginning. So we'll print conference as frozen, and let's freeze it. Yeah. So this is the only modification that we're going to make. So now we freeze the conference, and the thing which is returned by the producer is frozen. And we see that it works. And first, the conference is not frozen. We freeze it, it's frozen, and it works. And this is one of the restrictions that is put when you call the execute function. The producer, the value that is returned by the producer has to be either frozen, or it can be mutable, but you're going to see in a moment when it can be mutable. But if it's frozen, then it's safe to return it. So this is why it works right now. So what other things are frozen by default? Let's get back to our presentation. The other things that are frozen by default are objects. So objects are those singleton classes which are available in Kotlin. Companion objects, the same thing. And enumeration classes also are frozen by default. So what about top-level variables? They are quite similar to objects. Well, not objects, but they are accessible by many threads because they are top-level variables. So the question is how they behave. So let's get back to our example. Okay, and let's make this conference a top-level variable. So we're going to leave the rest of the application the same. No, actually, our producer will not return anything, and here we're going to access the top-level variable in our job. Okay, and let's see how it works now. The compiler itself, it's kind of slow right now. It's mainly slow because LLVM is kind of slow. The Kotlin native developers actually are working on it right now, but it is kind of slow right now. Okay, so we have an exception. And the exception says something like, oh, that's a long message. Let's try to make it like this. It's incorrect dereference exception. It's actually thrown here when you try to access the conference variable. And it says that trying to access top-level value not marked as thread local or shared immutable from non-main thread. So we actually were able to access conference from the main thread, so the thread that runs the main method. But we can't actually do it from a different thread. This is one of the restrictions. You can't access a top-level variable from other thread than the main thread unless you put one of those annotations, shared immutable or thread local. So let's see how they work. Actually, see how they work in practice. We're going to do one more thing. In the constructor of our conference, we're going to just print out that the conference is created. Conference has been created. Okay, and now let's add the shared. Let's first try the shared immutable annotation, and let's leave the rest of the application as it was before. So we have a top-level variable annotated as a shared immutable, and we also log the fact that the conference is created. So what happens? So first we can see that in the main thread the conference is created. So there's no surprise here. Then we can see that even before we freeze, the conference is already frozen. And this is because if we annotate the top-level variable with shared immutable, it actually does what it says. So it means that it's immutable, so it's frozen. Right after you create it, it's frozen. And it's shared because you can access it from multiple threads safely because it's frozen. So this is one of the ways to access top-level variables, and it's actually useful if you have things like, for example, configuration, and you want to keep it in a global variable. Then this is one of the ways to actually do it. There is one thing which you have to be aware about. Now, in Kotlin, we also have values and we have variables. And if we change this global property to be a top-level variable, like right now, we actually will see that we will get the same kind of exception that we had before. They are trying to access top-level value, etc., which is kind of misleading because we are actually trying to access not a value, but a variable, and it's actually annotated with shared immutable, but the compiler treats it as if it was a value not marked as shared immutable. So you have to watch for these kinds of things. So let's get back to our top-level variable, and let's try the other annotation, thread local. Let's see what happens now. So with shared immutable, we had conference which was frozen from the start, and there was one instance created only at the start of the application. And now what happens is that, okay, we have a conference created, which is no surprise, but then it's not frozen at the start of the application. We freeze it, then it's frozen. And then we can see that another instance is created in a different thread, in a different worker, in the worker that we start. And everything else works fine. And the reason is that what happens like this is that if you annotate your top-level variables with values with thread local, then each worker, each thread essentially, so either a worker or the main thread, will have its own copy of the object, its own instance. This is why you see here these two instances being created. Okay, so now we know how it is about top-level variables. So let's get back to our presentation. So top-level variables are covered. So the question is, what do we do with mutable objects? Because I said that we can have mutable objects, but they should be accessible by one thread only. And this comes with the concept of ownership. So in Kotlin Native, an object can be owned by at most one thread, and you can pass it between threads or between a worker and a thread. But at any single time, only one thread can be an owner of an object, and it can modify it or access it essentially. And this is actually the reason why we have this very strange signature of the execute function, because the object which is returned by the producer it has to be either frozen or it has to be a mutable object, but such a mutable object that doesn't have any references to it. Like when let's try to get back to the first example that we've seen. Okay, so at first we had this conference, which was a local variable of main, and we tried to pass it return it in the producer, and we tried to access it in our job. And okay, let's remove this thread local. And the problem here was that let's even not freeze it. So we have mutable, theoretically mutable object. It's not mutable because here we have values. Let's make it a variable. So we have a mutable object. We return it from producer, but there is a reference to this object from the main thread. So we have a reference which is kept here, and this is not allowed because now we have a situation where in the worker, we could access this object conference, but at the same time, we could do it in the main thread. So there was really, and this is not allowed in the Kotlin memory model, Kotlin native memory model. So what we can do instead is we can create this conference like we did before here. And here, this conference is actually mutable object. So we can actually mutate it here. So we can say, okay, let's make the year 2020, and let's even return it. So our job will now return the conference, the modified conference, and here we're going to print it out. So now the effect should be that we mutate an object in our worker, and this mutable object is returned from a worker and then accessed in our main thread. And it works. So this is actually the way to pass mutable objects from one thread to the other. So we create it here. There is no incoming references to this object. It's passed to this job, and this job returns it. And there is also no incoming reference to this object, so it can be safely returned and then accessed here in the main thread. So the question is, how is it done? There is something called detached object graph. So it's sort of like a wrapper around an object. This object can be mutable object, but when you create detached object graph, you can see here that the constructor is very similar to the thing that we use in the execute function. We have a transfer mode, and we have a producer. And transfer mode, by the way, it can be safe and unsafe. The difference is that if you put unsafe, then the execute function will not check these constraints that the object is either frozen or it's not frozen but doesn't have incoming references. So if you are sure that nothing bad happens, that you correctly pass an object, you can pass unsafe, because if you pass safe, there's some check done which has some impact on performance. If you pass unsafe, then there is no such impact. Can I get to the detached object graph? So that object graph itself is a frozen object. It's always a frozen object. And what you can do is you can create mutable object and wrap it around with detached object graph. And this way, you have sort of like a frozen object which can be passed to any thread and worker. And in that worker, if you want to access this mutable object, then you can attach it to a current thread. There is the attach function, which allows you to do just that. So let's try to do it in our application. So let's mirror display again. So we're gonna create a detached object graph with in safe mode. And we're going to create here this conference. Actually, we'll just copy here. OK, and our producer will return this graph. Graph is a frozen object, because detached object graph is always a frozen object, so we can do it like this. And here in our worker, we will just attach this to our worker, and here we can actually change it. Let's make it 2020. Let's put it here, and let's return this. So it should basically work almost the same as before, but now we don't return a mutable object from the producer, but we return this detached object graph, this wrapper around this this mutable object. And this is actually what happens under the hood if you just pass an object, return an object from the producer. It also creates detached object graph and then passes it to a worker, and then the worker attaches it to itself. Let's come back here. Let's get back here. Okay, so we have mutable objects, right? But now with the model that we've seen so far, there are some things which are not possible. And sometimes you actually need, if you want to, for example, create a cache of values, then you want to update this cache. Then what you want to have is like a variable which is available from multiple threads, but that you can actually modify it from multiple threads almost concurrently. So this is why you have these special types, special classes, which allow you to do that. They are quite similar to the ones you have on JVM. So for example, you have atomic int. An atomic int allows you to set the value or increase the value safely from multiple threads. And by the same token, we have atomic reference. Atomic reference calls a reference to an object, and you can call these functions to set the value and get the value from multiple threads. So let's try to use the atomic reference in our example to see how we can mutate a shared object with Kotlin Native. Okay, so we'll use actually the detached object graph we've had here. So we'll create a top-level variable which will be shared. We'll call it a conference ref. So it will be an atomic reference. And it will hold the detached object graph. Okay, so this will hold actually the detached object graph. So a frozen object which will hold this mutable conference that we have. And what we're going to do is, well, in our job will not need an input. But in our job, what we're going to do is we're going to first extract that conference from this global variable. So we have a conference ref. We get the value. The value of this atomic reference is the detached object graph. And then we're going to attach it to the thread. So we'll have a conference here. And then let's try to change something in this conference. Let's change a year. And now we have to put it back into this conference ref, into this top-level variable. So what we'll do is we're going to say, okay, so the new value will be detached object graph with transfer mode safe. And the value that this detached object graph will hold will be actually the value that we read from this reference, and we'll modify it and we'll return it. Okay, this may seem quite complex, but in a moment it will become clear. Let's also log it here. So let's log it here. Yeah, and that's it. So we don't really need to do here anything. So we modify it in our worker, and then let's try to access it in our main thread. So let's access it, conference ref, value attach. Main conf. So let's print this main conf. Okay. So we print the result. Let's make it okay. Okay, so what do we do here? We have a conference ref, a top-level variable. It's an atomic reference, so we can safely and concurrently in many threads read from it and write to it. And it holds these wrappers around mutable objects. And you can attach the object which is wrapped around which is in this wrapper to any thread. You can mutate it, and then you can put it back. So you can see that it actually happens here. We have only one instance of conference created here. We created it with the year 2019. Then we modify it here in our worker, and then we attach it in the main thread. In the main thread, we just print it out, and it's a changed object. So this is the way to have sort of concurrently modified shared state, shared variables. Right. So let's get back to our presentation. So all of this actually it allows us to have a garbage collector which doesn't have this property of stop the world pause. And this is because, like, if you have a thread which tries to allocate memory, and it sees that there is no memory available, so it has to run a garbage collector. It can actually run the garbage collector for that particular thread only. It doesn't have to stop other threads, because this thread will hold the references to either immutable objects, so it's quite safe to traverse the tree of those objects, or they are mutable, but only by this thread. So if a garbage collector runs on this thread, it means that they also will not be modified. So by having this property that you have an object either frozen or mutable by a single thread only, it's easier to write a garbage collector, and this garbage collector doesn't introduce these global stop-the-world pauses. The garbage collector, which is available in Kotlin Native, is actually based on the reference counter. So there's the counter at every object which contains the information about how many references are to this object. The usual problem with such garbage collectors is that they can't see cycles between objects, but the algorithms used by the garbage collector in Kotlin Native actually has support for cycle detection. So it's safe to use. And it's for those of you who will use Kotlin Native on iOS, nice property is that the garbage collector, which is available in Objective-C, the Kotlin Native garbage collector actually works together with the garbage collector of the Objective-C language. So it's quite safe to use it there as well. So there's one more thing left, which is native memory. Because if you use native APIs, then these native APIs sometimes needs like chunks of memory, like for example buffers for something. So the question is, how does it work with all of the things that we've seen so far? So let's try to use a simple platform API. We're going to read a file. I haven't done it in a while. I mean, I haven't programmed in C for a while, but in the C language, I'm going to just remove all of this. We're not going to use this anymore. In the C language, if you wanted to read from a file, you use things like fopen. Let's add some imports. Platform POSIX. All right. Where we provide the name of the file, we're going to read the Gradle properties. And I'm going to just read it. And this will give us a file. So let's close it at the end. And to read the contents of the file, we use fgets. Fgets as a function which has 3 parameters, which is, first it's a buffer. So essentially it's a pointer to a block of memory where the values read from the file will be kept. And then you provide the length of the buffer, and then the file itself. So we need a buffer here. So we have to allocate a buffer. To allocate a buffer, we will use something which is called arena. So with Kotlin Native, we have arenas to allocate native memory. So we create arena, and this arena will give us a possibility why doesn't it? To allocate an array. Where is arena in Kotlin X? C interrupt. Right. So this support for Kotlin Native in the IntelliJ IDEA is not that great. If you want to use it like more professionally, I would suggest using CLion. CLion is, I think there's no community edition, but CLion has a lot better support for Kotlin Native. Like it allows you to do things like debugging, for example. And as you can see here, this Kotlin plugin for IntelliJ is not, sometimes doesn't really work the way you would like it to work. Anyway, we have an allocate array function, which just allocates, we'll just allocate here a block of memory, and let's call it a buffer. And then, if you want to free the memory, you have to call clear. So this way you can allocate one arena, allocate a bunch of buffers, whatever objects you want, whatever chunks of memory you need in your application, and then you just call clear, and it will get rid of all of the memory allocated. So it's quite nice. So we're gonna use buffer here. Yep, and the fgets returns a line which was red. Now a line here is actually a pointer to an array of characters which is terminated with null value. But fortunately for us, there is a nice extension function called toKstring, which gives us a string. And we're going to do it in a loop. So if a line is null, then let's break the loop. Otherwise, we'll just print it out. Right. Okay, so this should work, I think. No, it's... Okay, let's remove this. Okay, so we allocate here the buffer. The buffer is reused for every fgets call. And we print out the contents of the file, which are actually these two lines. So it actually works quite nicely. And this pattern of usage of arenas, that you allocate an arena, you then use this to allocate a bunch of things, and then at the end you call clear. It's so common that there's actually a special function for doing these things, which is called memscoped. And memscoped allows you to remove this, and this. Okay. So now what you have is the memscope takes a parameter, a lambda expression, which has a receiver type of memscope. So memscope actually extends your arena base where you have all those functions for allocating memory defined. So this is why you can just call allocarray here. And when you exit the scope, then all of the objects, all of these chunks of memory which were allocated, they will be freed. So we don't have to remember to call clear, etc. So that's quite a nice way to do it. Yeah. So now with the memscope, it should work roughly the same. Yep. Okay. So yeah, this is about the interoperability with C. Now, to summarize it, we have one language, Kotlin language, but and we can use it on many platforms. And we have to remember that if we want to use it on Kotlin on the native platforms, things like Concurrency Model and Memory Model are a bit different, but they give you an advantage. And the Kotlin Native promotes using immutable objects, but the thing you get is safety, is safe concurrent code. Now, if you want to find more information, there are two places where you should go. The one is the official Kotlin Native web page on the Kotlin language website, and the other one is the GitHub repository for Kotlin Native, a compiler. You will find there also quite a lot of documentation and examples of many different things. And this is all from myself. I think we've just run out of time. So if you have any questions, I'm happy to answer them after this talk or during breaks. Thank you very much.